In this part of the lecture, we will be discussing the rotational dynamics of a rigid body expressed in the inertial frame. In our previous part of the lecture, we had worked out the rotational dynamics for a system of particles. Now, what we are going to do is impose a constraint on these particles, and the constraint is that the particles do not move relative to each other, or they are fixed with respect to each other. Their orientation may change. The collective orientation may change. This is what we call as a rigid body. So if it becomes it could be a continuum. In this case, we are still seeing a number of particles, but this continuum could be composed of a large number of particles. Now, on this rigid body, we'll call it the rigid body B, and on it we fix a frame given by this brown colored frame with the axis, brown colored axis. Here you have the origin, and deliberately the origin of this frame B has chosen to be different from the center of mass over here. Neither is it coinciding with the origin of the frame 0. We'll also assume that this rigid body is having an angular velocity. So the angular velocity is with respect to the inertial frame 0. Let's say that the angular velocity is omega. So omega of B with respect to 0. Now, what we did in our previous lecture was we worked out the rate of change of this quantity within brackets, which was called as the moment of momentum for all the particles. It was a summation for all the particles. So here you had the moment of momentum about the center of mass for this system. And here you had the momentum, and this momentum was with respect to the center of mass. So it was a velocity with respect to the center of mass. Now, when we make it a rigid body, the length of the vector from the center of mass to the point I, it does not change, because on this body all the points are fixed. This frame is fixed on the rigid body. So each of these vectors emanating from the center of mass, they are all fixed vectors, fixed magnitude vectors. And here you have the velocity of these fixed magnitude vectors, the rate of change of these fixed magnitude vectors. Now, since they are fixed in magnitude, the only thing possible is that they can change their orientation. So this velocity, we know from our previous lectures that this velocity for a fixed magnitude vector is given by omega cross r, or it can also be written as minus r cross omega, where r is the vector from the center of mass to the respective point I, and omega is the angular velocity of the body with respect to the inertial frame expressed in the frame 0. So the moment we apply this constraint, the angular velocity of the body comes into picture. So we can write this term here as a rate of change of, this bracketed term can be written as the mass moment of the momentum, that is the mass moment multiplied by this velocity, which is minus r cross omega. Now we can rearrange this. We can rearrange it. We bring this minus sign here, we shift this, and we have this particular form where we have the rate of change with respect to time. Here we have this term in the square brackets, and there's the angular velocity of the body B with respect to 0 expressed in the frame 0. Now let us see what is this term within this square brackets. This term here in the square brackets can be written like this. It's minus summation mi, and this r cross can be written as this skew symmetric matrix. This r cross is repeated 2 times, so we have this occurring twice. And when you carry out the multiplication, you get this matrix here. So very interesting matrix. You can see that the diagonal terms of this matrix, they are recognizable. They correspond to the moments of inertia. So here you have the moments of inertia about the x-axis, and this, it is as if this x-axis is passing through the center of mass, and it's parallel to the x-axis of the inertial frame 0. Likewise, here you have the moment of inertia with respect to about the y-axis, and here you have the moment of inertia about the z-axis. You can see that this is a symmetric matrix, and the off-diagonal terms, you can see that here they are very easy to remember, but these are called as products of inertia. So you have the moments of inertia along the diagonal, and you have the products of inertia. So this is a symmetric matrix, and because it's a symmetric matrix, it has real roots, and we'll discuss about the properties of this matrix in our subsequent lectures. We call this matrix as the inertia tensor, and this inertia tensor has certain special properties which we will discuss subsequently. So for the rigid body, we can write the left hand side as the rate of change of this particular term here, which occurred here, as equal to the rate of change of the inertia tensor multiplied by the angular velocity of the body with respect to the frame 0 expressed in the frame 0. You can see that this has similarity to the translational motion, where you are dealing with the rate of change of a particular momentum, which was the linear momentum. There you had mass multiplied by the velocity. But here you are having, instead of mass, you are having the inertia tensor. And instead of the velocity, you are having angular velocity. This product within the curly brackets is called as the angular momentum. And you can see that this inertia tensor, which was discussed here, it is the inertia tensor of the body about the center of mass of this body and expressed in the frame 0. So these two things are extremely important. The inertia tensor is about which point and it is expressed in which frame. That's clear from the components of this matrix. Now, because this body is going to change its orientation with respect to the inertial frame. These components x, y, z, which constitute this matrix, they are going to change. And because they are going to change, the inertia tensor is going to change with change in orientation. We will discuss about how the inertia tensor can be considered when there is a change of orientation. For now, we have got the rate of change of the inertia tensor multiplied by the angular velocity. That's the rate of change of the angular momentum of the body about the center of mass expressed in the frame 0. So the dynamics of the rigid body with respect to rotational dynamics, it can be written as the rate of change of the angular momentum of the body about the center of mass expressed in the frame 0 is equal to the resultant of the moments of momenta of these forces about the center of mass of the body expressed in the frame 0 plus the resultant of all the external moments given by the torques. We have considered p such moments that act on this rigid body.